Welcome to today's SCA webinar with PK Pandy of Texas Intercontinental Energy Resources on the topic of navigating CCUS, the landscape, historical context, opportunities, and participation. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I'm going to launch a couple of poll questions. The first one is, what is your primary discipline? So it looks like we got a pretty even mix between geoscientists and petroleum engineers, and a few in the other category, and a few facility engineers. So it looks like most of you have voted, so I'm going to share the results. We have 42% geoscience, 32% petroleum engineering, 21% other, and 3% facility engineers. So the next polling question is, how many years of full-time experience do you have in the upstream oil and gas industry? Votes are coming in. It looks like we have a good spread in the demographics across the board. Looks like everybody has more than a year experience, but some in every other category. Okay, most of you have voted, so I'm going to share the results. We have 11% in the 1 to 10 year range, 26%, 11 to 20 years, 26%, 21 to 30 years, and 37% have over 30 years experience. So before I introduce Mr. Pandy, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature. We will cover the Q&A at the end of the presentation, and you will be anonymous. So I'd like to share some slides here. So welcome to Navigating CCUS, the landscape, historical context, opportunities, and participation. PK Pandy is our speaker today. PK is founder and principal consultant at Texas Intercontinental Energy Resources. He has a wealth of experience in a number of different areas, deep knowledge in both commercial and technical solutions. He's got experience with gas injection, EOR, with CO2, CCUS, dealing with a number of other reservoir management topics. Previously, he served as chief engineer for QEP, and he was the director of reservoir technology at Anadarko Petroleum. He also worked at Total and BP. PK was a distinguished lecturer for SPE on the topic of shale resources, a full life cycle integrated approach. And he holds a BS in chemical engineering from UC Berkeley, an MS in petroleum engineering from New Mexico Tech, and he's a registered professional engineer in the state of Texas. So PK is teaching a class for SCA. That's a half-day course. It's offered in person on April 4th in Houston, Texas. So the webinar today will give you a taste of what will be covered in that course. We have some upcoming live online classes that are being offered soon. Bob Barbet is teaching best practices for new well fracs and legacy well refracs. This is a new date, so as not to conflict with NAPE. It's February 6th through 9th. And then we have Larry Lake and Jerry Jensen talking on managing mature oil fields with CRM, capacitance resistance modeling. In February and March, we have Dr. John Lee speaking on two different topics, production forecasting for low perm reservoirs and PRMS, SEC reserves and resource regulations. Those are both offered live online, and you can sign up now. In our webinar series, we next have, next week, in fact, Bill Ott and Jim Smolin. They will be speaking on cement evaluation and remediation. That's on January 31st. And then we have Amalia Olivia Riley speaking on optimization as a path to lower emissions, myth or reality. And that's scheduled for March 7th. So SCA training courses can come to your location. If you would like to offer our courses in-house, we'd be happy to discuss that with you. You can see the contact information there. And of course, in addition to training, SCA offers consulting, direct hire staffing services for both full-time and contract technical expertise, and we do projects and studies. And so I'm going to pass the presentation rights back over to PK. And looks like you should be able to present, PK. Great.
Very good. Thank you, Susan and Mary, for getting this started. Can everybody hear okay? Are we good on sound? And can everybody see the screen? I'm going to just go to full screen mode, and then we'll get started.
We can hear you, and we can see your slides.
Perfect. Okay. That sounds great. So let's get started. I'd like to go ahead and, okay, so the slides are not advancing. Hang on a second.
You may just have a lag. There you go.
We're good. Okay. 1 second here. I'd like to thank all the attendees for joining today. Susan has done a great introduction to the topic and my background, and we're pleased to have everyone. This discussion today, you can see the subtitle. It is going to have a business development focus. However, with a business development focus, it's going to have a very, very strong foundation with the geotechnical aspects. And also there's very unique regulatory aspects for carbon capture. So we'll be discussing that as well. So let's move into a little bit on setting the stage for the discussion today. And what we would like to kind of start with is looking at basically the foundational elements for carbon capture. There's a lot of historical context. There's a lot of foundational work that the industry has already done over the last 4, 5, 6 decades. So we'll discuss some of that. There's a lot of pieces here, and it gets pretty confusing. I call it the CCUS maze. We'll try to make some sense out of that. We'll try to look at some of that complexity, but simplify it so that we can actually deal with it. And so kind of my thinking on this is cutting through that chaos. We've discussed already that we're going to have a very heavy geotechnical and commercial focus. And as we think about CCUS in the industry, the typical thought process is it's about capturing the emissions, transporting it to a storage location, and then you've got the subsurface piece. There is a fourth piece that's actually very, very key, and it's the wells. And we'll talk later about why that's so important. But just to kind of plug that in real quick, there's a big regulatory component around the wells, and also they're very, very expensive. So in our discussion today, we've actually added this as a fourth component. And being able to integrate all these 4 components enables us to go ahead and do the full life cycle economic evaluations necessary to evaluate different projects and participation opportunities. So how we can use this thinking is, where do we want to participate? Why? What are the investments that are going to be needed? If you're on the funding side, what does that mean? We will talk about the Section 45Q credit. We'll explain what that is. That's really, really key. And then being able to use this for operational decisions as well. So this is an integrated approach. One of the other things that's really different about this approach is, yes, we need to look at the emissions that's at the front end of the cycle. However, the storage reservoir does really matter. And we're taking a petroleum systems-based approach here in terms of characterizing that and looking at how that plays into the whole project cycle and also for risk assessments. So CCUS does have global applications. You can see 2 different maps here. What we see on the left-hand side are existing operational projects. There's a very, very large number of projects in the North America region. And there's also a lot of new projects that are coming up, either in early development, advanced development, some under construction as well. Right now, the total capture capacity worldwide is about 40 million tons. But with the projects that you see here, we're looking at significantly increasing that. Although the applications are global, the solutions are local. So for purposes of our discussion today, we are going to focus on North America. However, within North America, we're going to focus on the Texas Gulf Coast region. And one of the reasons we're going to focus on the Texas Gulf Coast region is that there's a very, very heavy industrial presence here. There's a lot of existing activity, a lot of planned activity. So this is one reason we're going to focus on the Gulf Coast today. And what we do need to keep in mind, however, is the topics and the workflows and the discussions that we do have, they do have full applicability to onshore North America as well. And there's a lot of storage capability there. We'll discuss that, as well as other parts of the world. So here's an example of the CCUS maze. You can kind of look at this and read through this. There's a lot of pieces here, about the process, the emissions, where do you store this in saline aquifers for EOR, depleted reservoirs? How do you want to do this? Point source hub. There's really good work that's been done by SPE on storage management classification. We'll touch on that briefly. So as you look at this, what I'd like to point out is the items that you see on green. We're going to touch on those. Given the duration of the webinar today, we're not going to be able to get deep into all the different topics. So the ones that you see in yellow, we'll also touch on those, but not as deep as the ones that are shown in green. So that's our focus today. And again, the geosciences and petroleum systems-based approach is very key to how we're looking at this in terms of integrating all the different components of the carbon capture system. At the end of the webinar, we will talk about workflows, and that's really important. And because you've got all these different aspects that need to come together, how do you integrate this? How do you bring this together? And for that, there are workflows that are available, they have been developed, and we'll show some examples on how this looks like for the Texas Gulf Coast region, and they can be applied in other regions of the world and in North America as well. So just digging in a little bit deeper, some of the things that we will touch on today is we'll look at the historical context. What are we actually confident with, given that the industry has been doing gas injection projects already for many decades? Where should we inject? How should we characterize the sources? And what are the capacity needs? We'll look at that for the Gulf Coast region. How much CO2 actually, how much CO2 carbon actually needs to be put away. We'll talk about storage classification, the public policy drivers, and some of the regulatory challenges as well, and how we tackle the full cycle economics. So when we do all this, what we're coming up with are technical and economic screening criteria early in the concept and in the design and planning phase of projects or looking at a region to help us understand, hey, does this make sense? Does it not make sense from both a technical and commercial standpoint? And then how do we drill deeper as we move, from screening into the next level of analysis? So at this point, we're going to go back and look at some historical context. And for North America, we're going to look at two regions. One, I'm here in the Houston area currently, about as far away from Houston as you can get, on the Alaska North Slope above the Arctic, north of the Arctic Circle. And we'll look at projects in the Alaska North Slope. We'll also come back and look at some of the projects here in Texas focused on the Permian Basin. So what we do need to be cognizant of is that the industry has decades of experience in gas injection. And the gas injection projects that the industry has really excelled at is a class of recovery projects. What we describe in petroleum reservoir engineering is what is the recovery process. And this class of projects are called miscible gas injection projects. So for miscible gas injection projects, there's two ways to do them. One is you can use CO2, which is the same as sequestering carbon. However, you could also use miscible injectant. We'll talk about that. And that's where the projects in Alaska North Slope are based, because there's no market for the gas, but you can make miscible injectant, which behaves similar to CO2 in the reservoir in terms of swelling the crude oil, lowering the viscosity for additional recovery. For the projects in the Permian Basin, the CO2 actually comes from naturally occurring sources in New Mexico and Colorado, and we'll show that here in a little bit. In terms of the evolution, there was a lot of research done by major oil and gas companies, in universities, in federal agencies. Department of Energy didn't exist at that time, but the predecessor agencies. A lot of research in the 1960s, and the initial Permian project started in the 1970s. Really big projects implemented in Alaska for miscible injection in the 80s and 1990s. There are many other examples of this in other parts of the world as well, Algeria, North Sea, and others. But for today, we're going to just talk about the Alaska and some of the Permian Basin projects. So for the Alaska North Slope, these are some of the projects that are highlighted with the red stars. The two that you see circled are two that I actually had the privilege to work on in terms of the design, planning, implementation, and operations for Prudhoe Bay and for Endicott. Prudhoe Bay being the largest oil field in North America, and Endicott being the first Arctic offshore oil development in the industry. So for these two projects, what we want to demonstrate and discuss here is that the industry has a lot of capacity to do big industrial projects. Why is that important? For the Gulf Coast and for other regions of the world, these are large industrial projects. There's a lot of components that need to get together, that need to come together. And for Prudhoe Bay, just to give you an idea of the scale, the U.S. gas production currently, it's over 100 BCF per day, about 115 BCF per day. But the central CGF, Central Gas Facility, which you see here in the picture, this actually processes about over 7 billion cubic feet a day of gas. So it's roughly 6 or 7% of the total U.S. gas production in one facility. And I mentioned earlier that this is to be able to make miscible injectant in order to inject gas back into an oil reservoir for recovery. And of the gas that's processed, roughly 90% of that is then used, it's recompressed and it's used for reinjection. So the industry has a lot of experience in doing this. The bottom picture is a picture of some of the compression units that were built in the Gulf Coast area, Texas, Louisiana, and then went up by sea lift up to the Alaska North Slope. So the next area that we're going to go to is a little closer here to Houston, and it's actually the Permian Basin in West Texas. What we're showing here is one of the early projects implemented in the 1970s, the Denver unit for CO2 injection, miscible gas injection, again here with CO2. How this project is actually implemented in the reservoir is utilizing a technique called WAG, which is water and alternating gas. And the reason that you do that is to control the mobility of the CO2 so you get better contact and sweep efficiency in the reservoir. The main takeaway here is that we can actually implement carbon sequestration projects in oil and gas, not oil and not all, but in some oil and gas reservoirs for additional recovery. And we do have a wedge where we get additional recovery oil from how the field would have performed without doing enhanced recovery through just the initial depletion. And most of these fields have been water flooded as well. So with that, what we'd like to really do is next move into what are some of the processing facilities that are required for CO2 injection. So one is that you do need CO2 compression for injection. Again, this is something that's going to be needed in carbon capture projects as well to compress the CO2. However, in CO2 injection projects for EOR, you do have produced gas, and then this CO2 is actually purchased because it's coming from natural sources. There's pipeline transportation cost and paying the owners for the CO2 resource as well. And in EOR projects, you actually will go through a process where you recycle and you actually process the gas and recycle the CO2 for injection again. And the reason there's a big X here is that for CCUS and geological storage, that's something that's not needed. So again, these are learnings. These are things that the industry has done. It's done them really well. It's done them over a long period of time. So let's look next at the pipeline infrastructure for CO2 projects in the lower 48 or in the mainland US. I mentioned that the CO2 comes from naturally occurring sources. Two of these sources are from Colorado and New Mexico, what's known as the Sheep Mountain and the McElmwood Dome reservoirs. A lot of that CO2 is transported into the Permian Basin. For EOR, these red dots indicate projects that are happening in onshore US, and there's also a concentration in the Gulf Coast area and some other parts of the country. There's roughly 5,000 miles of CO2 pipeline currently in the US. This CO2 typically is transported in what's called in a liquid phase, which is past the critical point. And what that means is that we want the CO2 to be dense, but we want it to have properties of a gas. We want to have good viscosity, but we want to be able to keep it in a liquid phase so we can transport a large volume through a pipeline network. There are estimates from a lot of the planning work that have been done by policy agencies and also the Department of Energy and other federal agencies on what pipeline network will be required as we move into much more broader carbon sequestration projects. And those estimates range anywhere from 25 to 50,000 miles of additional pipeline. That pipeline is regulated by an agency within the Department of Transportation called PHMSA, PHMSA. That stands for Pipeline and Hazardous Materials Safety Administration. Pipeline transportation is a very regulated industry, both worldwide and in the US. And so there are some specific regulatory aspects for the pipelines as well. So what we're going to discuss next is we're going to get into just a summary of what CO2 EOR and miscible gas injection has already taught us for carbon capture, and especially aimed at geological sequestration. So these technologies that I've discussed briefly, they are directly transferable. That's really important. The industry's got experience. The industry has confidence. Not to say that there won't be differences, there are, but there's a lot of established things that are already available. The other thing that comes up with respect to carbon sequestration is, and this is in the regulatory work as well, is answering this question of will there be cap rock breaches? And what we do want to be able to confidently say is that with a proliferation of many dozens and dozens of miscible gas injection and CO2 injection projects and other types of processes as well, nitrogen injection, there have been no detectable cap rock breaches. What do you introduce into the system is wells. So it's important that the well construction, it be done well, good cement jobs. We don't want to have surface issues and so forth, but this does come into regulatory. But as far as the geological aspect of this, no cap rock breaches. So that's good to know. One of the other things we need to be aware of is that timescales do differ. For miscible injection and CO2 EOR, we're looking at projects that may typically have a project life of 10 to 30 years, something like that. With carbon capture, we're looking at sequestering, the carbon for hundreds of years from a practical, basis with the technology we have, and the regulatory aspects that need to be satisfied, 100-year plus, several hundred years, so the timescales are different, and we need to be aware of that. And that does come into play as we work some of the well permitting aspects of carbon capture for sequestration. One of the other things that's really key is that boundaries do differ. For oil and gas reservoirs where we do EOR and injection of miscible injectant or CO2, we typically know the boundaries of the reservoirs pretty well. With respect to an injection into what would be a saline aquifer, it's a different reservoir system. It could be much larger. So we need to be aware that the external boundaries may be different and how that CO2 behaves over a longer period of time and the plume development and how it spreads. So there are tools that the industry has to help us model that and to look at what those possibilities are, but that's something that we need to be aware of. And with that, I mentioned sweep efficiency before. For oil and gas recovery, we do want good volumetric sweep. Typically we want to channel, the injectant through a very confined area or pattern of wells. With respect to sequestration, there's no offtake point. So how that moves, what that sweep looks like, that's going to be different. So that's one of the differences for geologic sequestration. Another difference is that the source of CO2 differs. We talked about the naturally occurring CO2 for CO2 injection, using miscible injectant where there's not a market for putting that gas in the pipeline to re-inject back into oil reservoirs. For carbon sequestration, the gas source is going to be coming from industrial sources predominantly, and the concentrations are going to be very different. So we'll talk about that a little bit in the economics. So that's a difference. And then with that, one of the most important differences are the economics. And with respect to EOR, you do have a revenue stream from the oil that's produced. So that changes, the economic model. For carbon sequestration, you're putting a carbon and CO2 into pore space for a long period of time. And so the economic model on how this all works is a little different. We'll discuss how the Section 45Q tax credit really enables the industry to do a lot of a really hard look at how to accelerate some of these projects and be able to actually make them happen. So one of the other differences too is part of the motivation from a public policy standpoint of the 45Q is to help reduce the greenhouse gases. And just to be aware, when we do this for EOR, we're producing hydrocarbon oil, additional oil. And so I think just being aware of what that carbon balance looks like. There's also CO2 retention in the reservoir. So there's some differences there between direct sequestration and for EOR. And finally, to sum this up, is these are complementary technologies. So as an industry, let's leverage what we know. Let's understand what those differences are, and that will help us to accelerate the implementation of many of these projects and also look at where these opportunities are. So the next thing I'd like to show here is where should we inject? We talked about for today, we're going to focus a little bit on the Gulf Coast. And we'll look at this here in a little more detail. But one of the geological storage opportunities that we do have in the Texas Gulf Coast region is what's called the Miocene reservoirs, and these are shown in the isopacks here in the green across the coastal areas of Texas and Louisiana. There's a lot of storage capacity there. We'll discuss what that is. But just to kind of ground ourselves, why do we need to look at the Miocene? Even though we can sequester in oil and gas fields, we can't do it in all of them. They do need to meet different technical criteria in terms of quality of reservoir, thermodynamics, and so forth. And if we look at all the CO2 that's been sequestered to date in the U.S. so far, it's been about 11 trillion cubic feet, less than a gigaton. And the types of volumes that we do need to sequester, both in the Gulf Coast, in the U.S. and worldwide, are a lot larger. So although EOR can play a role, it's not enough. So we need to look beyond that. We do show here where where some of these pipelines are, for CO2 going to different fields. And the blue, we show some of the emissions sources for the industrial emissions. The red line here, it shows the boundary of the state waters for Texas, and then beyond that we get into federal waters. There actually has already been a lease sale by the Texas General Land Office for Texas lands in terms of offshore sequestration, and there are some additional ones that are planned in the future. And in the federal side, BOEM, which is the regulatory agency, Bureau of Ocean Energy Management, are looking into the leasing framework for leasing for offshore storage in federal waters. And I think I'd mentioned this already. So the other piece of this is that if we look at saline aquifers just for Texas Gulf Coast, there's over 2,000 gigaton storage available, whereas for CO2 EOR and depleted fuels, yes, there are opportunities. It's not to say that those projects can't happen. There will be opportunities there. That's going to be very local, field specific. One thing to understand on EOR is there are no active EOR projects offshore in the United States, and there's some reasons, for that. And most of the EOR, actually all the EOR in the U.S. is in onshore reservoirs. So let's dig a little deeper about the Miocene. And what we're going to do here is we're going to show a geologic cross-section going from Texas land, onshore region, into the Gulf of Mexico. This is kind of what the cross-section looks like. And then we can look at this in the top view here, is we're starting from land, onshore, getting into state waters, and then getting into federal waters. And with respect to the Miocene, that's a large storage resource that's available for geologic sequestration. And what we had mentioned earlier was that when we do store into the geologic formations, there are some thermodynamics that we need to be aware of. And to kind of simplify this, we need to be at a suitable depth and temperature where the CO2 is dense, it's in liquid form, so that we have high density. However, we want it to behave like a liquid. We want it to behave like a gas, viscosity that's low, and that's the supercritical point. And this red line typically generally shows what type of depth we need to be at in the Texas Gulf Coast region, moving offshore, and for temperature to be supercritical. So that's actually important. And we've highlighted here this Texas state waters and then going into federal waters. So again, in order to actually do the geotechnical screening and the petroleum system-based screening, there's a lot of different subsurface aspects that come in on the geological side, geophysical side, geochemistry, petrophysics, thermodynamics, petroleum reservoir engineering. And it's important that all of that be considered in the evaluation process and in identifying storage, suitable storage areas. So not all rock is created equal. What we are showing here is what that storage potential looks like in state waters. And here, I think the way to look at this scale here, going from red to gray, red, it's better reservoir, it's better rock. And however, that doesn't preclude storage from not happening in other coastal areas. This is just a Texas Gulf Coast, Louisiana is not here. But in the state waters, roughly 30 gigaton of storage is available. When we add the federal waters to that, it's about 125 gigatons. These are what some of the estimates are. But already mentioned before, the total EOR sequestration that's been CO2 that's been sequestered from CO2 injection is less than a gigaton. So it's a huge storage resource that's available. And to kind of give a little bit of grounding, what the units when we start to work in carbon capture, they're different than say the typical oil field units we may be used to in other units. But when we're talking about a gigaton, that's 1 billion tons. And so if we have a single well that injects, say, roughly 50 million cubic feet a day, the actual number is about 53. That represents about 1 million tons per year. So a huge storage potential in the Gulf Coast. Next, we're going to get into how do we actually characterize some of these storage resources. And so with that, the US global emissions, the global emissions with respect to CO2 is about, it's about 36 gigatons a year. These are some of the numbers are available, and about 3 in the US. For the Texas, Louisiana coastal area only, we're looking at about 200 million tons per year. For Texas, Louisiana, the statewide total is about 550 million tons per year. The Gulf Coast is a highly industrial area, so about 30% of those emissions are coming from power plants. Whereas if you look at the United States as a whole, about 60% of the CO2 emissions are from power generation for electricity. It could be coal, it could be natural gas. That's what we're looking at. So for the Texas Gulf Coast, it's still, from a regional perspective, there's still a lot of CO2 that's generated. These different yellow dots that you see is just a scale of different industrial sources for the CO2 and how much the value of that. The larger the yellow oval, the larger the amount of CO2 that's generated. So if we look at 2 of the core industrial areas, which is along the Houston, Port Arthur, Freeport, Galveston area, and the Mississippi River Industrial Corridor, they're very, very heavy concentration of chemical plants, refineries, and so forth. That comprises over half, it's about 55% of the total emissions in the Gulf Coast area. And we have seen already several projects that have been announced, others that are being looked at, for these areas. So this kind of gives you a sense of how to characterize. There's data available on each and every individual facility, and that can be aggregated and looked at on a regional sense, and other ways to actually look at that for a data-driven type of approach on characterizing the emissions. So next, I want to touch on this. There's a public policy agency called the Kearney Institute. So this information is coming from them. And what we see here are the projects in gray that are currently in progress, available. It's about 40 million tons per year. And the purple, what we see, this is worldwide, we see projects have been announced. And the key takeaway here is there's still a lot of work the industry needs to do. This red, and you can see what the numbers look like, is there's a lot of additional CO2 capture and storage that's required to meet what's called IEA, International Energy Agency, Sustainable Development Objectives. And that's really to get to net zero by 2050. So that's what we're looking at here in terms of the capacity needs and what's out there and what's needed. We're going to move next into some of the regulatory challenges. And what we show here in this diagram are the different types of injection well permits that are needed. For existing oil and gas operations, most of the permitting that's done is what's called the Class 2 wells. The Environmental Protection Agency has made a separate classification for geologic sequestration of CO2, and that's called a Class 6 well. And EPA regulates the permitting. They can have the states do this with primacy, giving permission to the states. And currently 2 states, Wyoming and North Dakota, do have primacy from the EPA to issue permits. So there are many new projects that are happening in different parts of the country. And so there are several states that have applied for primacy: Texas, Louisiana, West Virginia, and Arizona, which was interesting. But the story there is there are native Indian lands that are available for storage. So I think that's what's behind that. The time that it's taken to approve the permits that have been awarded to date have been pretty long in terms of a sequestration type operation. It's taken 4 years plus. We do expect that to be shortened. At this point, only 2 Class 6 permits have been approved. However, as there is more work in this area, there are more resources that are being put into the permitting process, and we expect that to shorten. However, even with that, the expectation is that although, yes, this permitting process will improve, it will still take quite a long time. So if you are thinking about a sequestration project, this is something that is on the critical path in terms of geological sequestration. So why is it that it takes such a long time, and what is it that's different than, even though I'd mentioned earlier, the industry's got a lot of experience in injection wells? Well, what's different here is you're sequestering CO2. The EPA would really like to have a lot more data. Even before drilling a geologic storage well, there's data wells that may be needed to get the appropriate data to characterize a source. EPA requires an area of review be defined. And unlike typical oil and gas operations that the industry is very familiar with, there are very, very extensive geotechnical modeling that's required on what does that plume movement look like over decades, 100 years, 200 years. What does that look like? And so there's a lot of geotechnical work and getting the data to do that that's required. That's part of the permit process. In addition, even after getting the permit, you need another permit to actually do the operations. There's a permit for the construction and so forth, but then for the operating. And then there's also very extensive work that's needed on monitoring, different techniques, different things to actually be able to monitor that the CO2 that you're sequestered will actually stay where you think it will. So that's pretty important. Real quick, I want to mention this is from the Society of Petroleum Engineers, and just as we have for proven, developed, undeveloped, contingent oil and gas resources, the SPE has actually come up with a classification system for CO2 storage geologically, different resource classifications. The general kind of concept is this is a lot of the screening and lead generation and looking at prospects. But to get to move up on this to the top where you want to be, you want to have storage capacity. You need to have the wells in place. You need to have a final investment decision, so on and so forth. So this is something that the industry will need to be working with. The SPE has convened this group again to update and to keep this current. And the Department of Energy is now looking at this in terms of how that can be utilized on a more broader sense as well. We're going to move next into the Section 45Q tax credit. This is really, really important. And so the IRA, Inflation Reduction Act legislation, which was passed by Congress last August, this is actually going to provide a big thrust, a motivator for kickstarting CCUS even further in North America. What we're going to show here is just a quick synopsis of what did it look like before the IRA legislation, afterwards. So you have more time, more money. So you can see the construction start times. There's several more years to do so. The sequestration credit is a much higher, both for direct sequestration and for EOR. There's some additional requirements for wage and apprenticeship to allow for employment. So there's some requirements there. We're not going to get into direct air capture today. That's when you're looking at capturing CO2 directly from the atmosphere. That's in parts per million from streams as opposed to percent or much higher. But there are provisions in the IRA legislation as well for direct air capture. There's also much better flexibility, greater flexibility in which facilities qualify. So for power generation, you can go to much smaller facilities post-IRA. With direct air capture, much smaller facilities as well on the direct air capture size. And then in addition to power generation, we can look at other industrial facilities that are much smaller than before the IRA legislation. One of the other things that the IRA legislation does is it gives much more monetization options. And so there's a time period to get the credit depending on what type of entity that you're in, what's called a direct pay. However, what's really powerful is that these can be transferred, they can be sold. So that's actually a very, very powerful commercial tool in terms of monetizing earlier the 45Q tax credit. And there's some other means as well in terms of being able to monetize this credit available from the US government through what's called private action bonds. So let's talk a little bit about costs. The costs vary a lot. They're very location and project specific. The big part of the cost on this is on the capture side. The transport, some of these other requirements are there, the storage is there. Why this purple bar is so broad and so big on the capture side is it depends on the industrial facility. It depends on how much CO2 you have in that facility. Is it hydrogen? Is it cement? Is it steel? Is it a refinery? What type of facility do you have? What type of process you have? And what we should highlight in the green here is what that 45Q tax credit looks like. So with all that, we can take these costs. There are tools available to help do some of the screening work, looking at the capture, transport, sequestration to help do the full life cycle evaluations. I'm going to move next into how do we bring this all together. We talked about navigating CO2. We talked about the CO2 maze. So, and we've touched on a lot of these elements. So with the petroleum systems-based approach, the way that one way to go about this and the workflow that's available to really look at this, first we start on the capture side. We look at the volumes, we look at the long-term outlook, how it's processed, how do you want to do this, a point source, small hubs, bigger hubs, the long-term outlook, you know, what that looks like. So that's on the capture side. However, next, we're going to jump immediately into the subsurface storage. And why we're going to do that is we need to look at, you know, for example, in the Texas Gulf Coast area on the Miocene, well, how many projects do you need? What are the sizes of those projects? Realistically, what are those reservoirs look like in terms of size? What type of development timing, reservoir conditions, how far are you from shore, which is going to impact, you know, the infrastructure. So that's kind of the next step in this process. Moving next into the pipeline transport is we've got the two ends covered on the capture, the subsurface, what's the infrastructure you need on the pipeline, the compression, the sizes, the rates, the networks. And once we do that, then we get into the well construction. And you ask, well, why? Well, I mean, you need to have these other three components to really look at well timing. How do you want to bring this into a development? How do you actually want to mitigate some of the subsurface risk because you get more data by drilling wells? And so looking at the timing, the injectivity, we've discussed the permitting, how that's a critical path issue. Doing all that, again, we can jump into the economics. So finally, what I'd like to leave you with is that this is a fully integrated system approach. This is how we take the maze out of CCUS and make some sense out of it. We can extend these workflows, not just for the Texas Gulf Coast. What I've circled here, there's about 37 geologic basins onshore US that have been identified for sequestration. I've shown 7 or 8 here. These specific basins, and there are others as well that someone may have interest in. it represents about 85% of the storage capacity for lower 48 US. So finally, closing thoughts. So getting, in terms of CCUS for geologic storage, securing storage sites is very key. It requires a petroleum systems-based exploration kind of mindset. A lot of geoscience capabilities are very, very critical to that. Industry's got a lot of experience. We've talked about that extensively today. The 45 tax credit, it's huge. It's important. It's going to be really, really key. In fact, I've heard that even relative to the other parts of the world, in some ways, you know, North America, the U.S. specifically, this has really, you know, I mean, been a big boost in moving carbon capture for geologic sequestration ahead. So that's a huge piece of this. And we talked about the capture piece. We didn't get much into the processing, some of the process engineering, but that's a pretty major piece of the whole value chain as well, and the regulatory challenges. So with that, we've talked about those workflows to be able to integrate all this. And I hope that the comments today, it gave you a few of these learnings and appreciation for what's involved. And with that, I think, Susan, I'm going to bring it back to you, and we can have some time for discussion. And I want to thank all the participants for being here today.
That's great, PK. We've gotten a number of questions in our Q&A box here. So first, let's talk about clastics and carbonates. What are the differences of the CO2 EOR techniques applied for siliciclastic and carbonate reservoirs, and what are the advantages and disadvantages in each type of reservoir?
Okay, so the geology. Okay, so I've got the saying for CO2 EOR, which I think is what the question is. Geology matters. So there have been different formation types that miscible injection and CO2 have been applied to. Many of the projects have been in sandstone reservoirs. There have been projects in other geological types as well. One of the things that you need to be really careful about is the presence of natural fractures. So if you have that, that will end up causing a situation where you have premature breakthrough of CO2, so that needs to be considered. So it can be implemented in multiple geological type of strata. However, it needs to be characterized to ensure that you have good sweep efficiency, and I think breakthrough of CO2 would be another key consideration.
Great. Next question. How can one detect cap rock breach if there is such?
So one of the things I think that really comes to play here is having pretty strong data around the geomechanics and what that actually looks like. There will be extensive pressure monitoring that's required as a part of the monitoring process on the Class 6 wells. So I think understanding the geomechanics and what that looks like, and being able to do the surveillance and the monitoring to be able to ensure that you're operating in a reasonable level. To do a cap rock breach, it's going to take a lot of pressure. So I think it's, at least my interpretation of that is, it's going to be really difficult to get there. I think what's really more important in terms of a breach is looking at the wells that you have, and that's probably your bigger risk. And the cements that you have and the well construction, I think that's going to be much more important than the cap rock.
Next question. Next question. What are you hearing about the U.S. federal government's progress towards both leasing pore space in federal waters and also promulgating the rules governing such operations?
So the BOEM, I mean, there is not a framework yet for the federal waters. they are working that. I think there's good news and news. I don't want to say bad news, but there's good news and news. The news is they're working on it. It's going to take some time. I don't know how long. I mean, I think Boehm needs to answer that question, but it could be 2 years. Maybe it's less than that. Maybe it's a little more than that. The good news is there's a lot of work that you can do ahead of time to position yourself on how you want to participate in this. So that will come, but I think when you really want to think about what do you want to do, how do you want to do it, how do you want to participate, is you need to start working on that now. The rules will come and they'll evolve, but it's going to be a while, and I think Boehm is working on it.
Next question, what are your views on how the EPA and states with primacy will view depleted reservoirs as carbon storage projects, given the typically large number of legacy wellbores in these reservoirs?
Okay, there are a large number of legacy wellbores. I think one of the real powerful and advantageous aspects of going into an existing depleted reservoir is that you've already characterized it. You've produced it, there's wellbores there, you've got a lot of data. In terms of implementing a project, I think from a facilities, well construction standpoint, I think that needs a hard look. CO2 is very corrosive, so having the right types of metallurgy in the tubulars and the steel and the facilities, so that may need to be reworked. However, storage into depleted fields, there's no reason that it can't happen. However, I think you need to look at kind of the full project and all the different components to look at how do you actually bring that together. Again, the most powerful piece is what that reservoir looks like up front. You don't have to go get additional data to understand that as you would, or go get a lot of new data as you would in a Miocene storage situation where you've got to look at seismic, you may need to drill some test wells, and so on and so forth. So you've got a big lug up on that.
Okay, we've got a tax question for you. Would a midstream capital investment to capture flared and or vented gas qualify for the tax credit or Section 45Q if sold? If not, if injected into a subsurface reservoir, would that make it qualify?
So in order to get that 45Q credit, my understanding of the legislation is it actually needs to be sequestered. Now there's different ways to do it. You can do it through geological sequestering and in the storage site. You could use it in EOR, the credits change. But in order to get the credit, you actually have to capture that CO2, capture those emissions, and you have to sequester it. So this question is good. It's brings up an interesting point. Is the commercial aspects of a project like this, they are very complex because one, there's a lot of different parties involved. There's a lot of different elements involved. So I think the short answer, I think, to the question is you've got to sequester it, but I think each situation would need to be looked at. If it's being emitted right now, it's flared and then it's captured and sequestered, it should qualify for the 45Q credit.
Okay, somewhat related question. I think this is a legal question. Can the 45Q tax credits be applied to an international project with a parent company incorporated in the U.S., or does the project need to occur in the U.S. to benefit from the tax credit?
My understanding of the 45Q legislation is that these projects are to be in the United States to qualify for the credit. I mean, I think other countries have their own things that they're doing. So this credit would have to apply for a storage site in the United States.
Okay, I think this is probably our last question we have time for. How will the EPA be able to scientifically judge submitted plume diagrams and engineering reports?
So the plume diagrams and modeling and the simulation, these are all models. These models incorporate a lot of it incorporates geology, it incorporates flow of fluid through porous media, and basically it requires data. And so I think in order to be able to demonstrate this to the EPA, you need I think there's a lot of very deep technical due diligence that's required in terms of doing these models and then being able to communicate the results of those models. I think what's really key here, it's not one outcome, it's a range of outcomes, and looking at the things that you do know well, the things that you don't know well, what those range of possibilities are, but then being able to demonstrate that range of possibilities, even on a downside case, it's acceptable in terms of the risk. So I think back to trying to answer the question, deep technical due diligence with subject matter experts integrated real well into that whole modeling process. That's really key. There are some really good tools out there. There's multiple tools. It's about the data that goes in, and it's about the interpretation and the application.
Excellent. Sorry we couldn't get to all the questions today, but we'll make sure PK has a chance to answer them offline. So thanks for attending today's webinar. Later today, you'll receive a link to the recording of today's webinar, an evaluation form, and a link to SCA's website with more information about navigating CCUS in the Gulf Coast region, opportunities and participation, a half-day course that's scheduled for April 4th in SCA Training Center in Houston, Texas. Thanks very much. Goodbye.